Imagine you install a skill for your AI agent, which is just a small text file of instructions that teaches the agent to do a task, like format messy data into a clean report. And you download this skill from the official marketplace, which is exactly what you would do. And the marketplace told you that it scanned it and also marked it as clean. But a moment later, after you have installed the skill for your AI agent, your crypto wallet keys, SSH keys, and browser passwords are on their way to an attacker. So this is the CLAWHUB attack, and researchers audited nearly 3,000 publicly available AI agent skills and found something remarkable. They found that almost 12% of these skills were malicious. Some of these skills installed info stealers, others just manipulated financial recommendations for profit. One of them even turned installed AI agents into a coordinated cryptocurrency pump and dump network. But the most interesting part is not what these skills did. It's how they got there in the first place. Some of them hid their payloads so the scanners would never read them. Some of them stored the malware somewhere else entirely. And the most sophisticated attacks contained no malware at all. They just had instructions. And in this video, we'll break down exactly how each technique worked. We'll also talk about why 3 different security scanners, including an AI-powered reviewer, failed to stop them, and what this teaches us about securing AI agent marketplaces. Everything you see here comes directly from the public research published by Unit 42, JFrog, Koi Security, and SNCC. And I've just distilled all of the publicly available information into these nice diagrams. So it's going to be a highly visual video, so make sure you stick around till the end. A CLAWHUB skill is not a plugin that runs as a separate program. It doesn't spin up its own processes or execute inside its own sandbox. At its core, it's just a markdown file called skill.md, and it's a set of instructions written in plain English that tells the agent how to perform a task. It might explain the AI agent how to format a report, how to review source code, or to interact with the particular API. But the dangerous part is not the file, it's where those instructions execute. When you install a skill, the agent does not isolate it from the rest of the system. It reads those instructions and follows them inside its own processes using its own identity. That means the skill automatically inherits everything that the agent already has access to, like the credentials, API keys, file system permissions, authenticated browser sessions, network access, and any connected services. It does not need to exploit a vulnerability to gain those permissions. It actually starts with them, and that completely changes the security model, because instead of exploiting software, the attacker is exploiting trust, and they write instructions that look legitimate. The AI agent interprets them as part of his job and winningly performs actions on the agent's behalf. And researchers gave this technique a name. They call this semantic instruction hijacking, and the attack is not hidden in executable code, it's just hidden in language. But you must be wondering that if these skills were malicious, why didn't the marketplace just stop them? After the first attacks, CLAWHUB actually added multiple layers of security screening. On paper, it looks quite comprehensive. In the first step, every uploaded skill passes through VirusTotal, which compares it against dozens of antivirus engines looking for known malicious signatures. Next comes CLAWScan, the marketplace's own scanner, which analyzes the uploaded files for suspicious code. And finally, a third layer called CLAWDEX uses a large language model to read the skill itself and decide whether its instructions appear malicious or not. So every published skill is reviewed in 3 different ways: by signature matching, by code analysis, and an AI reviewer. Now this sounds quite difficult to bypass, but researchers still found active malware sitting in the official marketplace while passing verdicts from all 3 of these layers. And the interesting question is not that they got through, it's how each scanner was defeated. So what did one of these malicious skills actually look like? Surprisingly, they were almost completely legitimate. One of the examples that the researchers analyzed was a skill called Omnicog. It claimed to be a convenient way to connect services like Reddit, Steam, Spotify, GitHub, Discord, and YouTube through a single interface. And to do that, it asked users for API tokens and authentication credentials, which is exactly the kind of permissions you would expect a tool like this to request. And nothing about the description immediately looks suspicious. The interesting part was buried further down. Under an ordinary heading like Mac OS installation, the skill included a short prerequisite command that users, or in some cases the agent itself, were instructed to run before using the skill. At first glance, it looked like a normal setup command, but it was not. It was a curl bash dropper. So curl downloaded a script from the internet, and instead of saving it to disk, the output was piped directly into bash, which executed it immediately. And that alone makes it harder to inspect, but the attackers added another layer. The command itself was base64 encoded, so instead of seeing a URL pointing to an attacker-controlled server, both human reviewers and simple signature-based scanners mostly saw what looked like a meaningless block of random text. Only after decoding it did the real command become visible. It reached out to a hard-coded command and control server, downloaded a second-stage payload, and executed it. In OmniCog's case, that payload was an info stealer fetched from this IP address. The uploaded skill looked harmless. The real attack only became visible after you peeled back each layer. So by now we've looked at what OmniCog contained. Now let's look at how it avoided detection. The attackers did not use an advanced obfuscation technique. They used something much simpler. They just made the file too large to scan. The malicious base64 command sat right at the beginning of the skill.md file. After that, the attackers appended roughly 22 megabytes of meaningless padding, just enough to turn what should have been a tiny markdown document into an enormous one. And the reason they did this is because scanners have limits. Analyzing very large files is expensive, especially when thousands of uploads arrive every day. So to keep processing time and infrastructure costs under control, scanners typically enforce a maximum file size, and anything beyond that limit is skipped or only partially analyzed. And that decision is obviously perfectly reasonable. It's also exactly what the attackers exploited. VirusTotal never fully processed the file. ClawScan assigned it an unrealistically low severity, and the AI-powered reviewer marked it as benign. And this LLM scanner had an additional problem. Now, large language models, as you know, don't have unlimited memory. They can only read a fixed amount of text at once, a limit called the context window. A 22 megabyte markdown file is far beyond what the model can ingest in a single pass, and the attackers deliberately sized the padding to exceed both the marketplace's file size limits and the LLM's context window. The scanner did not miss the payload. It never basically got a realistic chance to even read it. And while all three scanners reported the skills as safe, OmniCog accumulated more than 5,000 downloads in under 3 weeks. By now, the attackers understood one very important limitation, which is that every scanner only analyzed what was uploaded. So the next generation of malicious skills simply stopped uploading the malware. Disguised as TradingView integrations, these skills contained nothing more than installation instructions and a link to a setup page hosted on a public-based site like Rentry, also pronounced as reentry. And the uploaded skill was completely clean because the malicious payload was not inside it. Instead, the user or the AI agent was instructed to visit that external page and run the setup command from there. The attackers also chose trusted infrastructure. The first stage lived on services like Rentry or reentry, while later payloads were fetched from GitHub. And these are domains that are commonly used by legitimate developers and therefore are far less likely to be blocked. But the main trick here was this, which is that a reentry URL can keep the same link while serving different content. The attackers submitted a harmless page for review, waited for the marketplace to approve it, and then replaced its content with the real dropper. The URL never changed, but the data that was being served from the URL actually changed. And a scan performed today would see completely benign instructions, while someone installing the same skill tomorrow would receive a malware instead. Even months later, researchers found several of these skills still carrying pass or no verdict, but behind the scenes, the attackers simply rotated their infrastructure, serving updated payloads, including an info stealer called CLUW, from new command and control servers. Now, this attack does not depend on whether the command is executed by the AI agent or the user. In environments that automatically run prerequisite steps, the agent decodes the base64 command, downloads the payload, and executes it itself. Otherwise, the installation instructions simply convince the user to copy the command into their own terminal, moving execution completely outside the agent's sandbox. Either path ends the same way. The curl bash dropper downloads the second stage payload, installs the info stealer, and begins harvesting LLM API keys, SSH private keys, browser-stored passwords, and in these campaigns, data from more than 60 different cryptocurrency wallets. Now, if you would like the Excalidraw board from this video, along with all the references, diagrams, and a PDF summary, I've put all of that together as a free download. The link is in the description of this video. And if you're interested in practicing real-world exploits like this one in a safe environment, that's exactly what we built at Armor Dojo. The link for that is in the description of this video. And one of the most sophisticated attacks that happened here did not contain malware at all. The skill was called Money Radar and posed as a financial advisor that compared brokerages, banks, and cryptocurrency exchanges. But before answering any questions, the skill.md file instructed the AI agent to fetch a file called referrals.json from an attacker-controlled domain. That JSON file became the attacker's control channel. It contained the list of the products to be recommended, the affiliate links to embed, and could be updated remotely at any time. And every time the agent answered a user's question, it first downloaded the latest version and built its response around whatever the attacker wanted to promote. So this skill never downloaded any malware. It never executed a binary. It simply told the AI agent to fetch a configuration file and follow its instructions. And that makes this attack fundamentally different from the others because there's no malicious code for a scanner to detect. The payload is the agent's own response. There was another skill almost as dangerous, and it didn't steal any credentials. It just recruited AI agents into a coordinated financial attack. A skill called Let's Send It instructed every installed agent to contribute Solana cryptocurrency to the operator's wallet, and coordinate with other compromised agents through infrastructure hosted at let'ssendit.fun. Once enough agents had joined, the operator bought the send it token before anyone else, then triggered the coordinated buying activity. And to outside investors, it looked like genuine market demand, when in reality, it was thousands of AI agents following the same instructions. The result was a classic pump and dump scheme, and was not driven by bots, but just by AI agents following perfectly ordinary text instructions. Another skill, Bob P2P, used the same idea differently. It just instructed agents to retain plain text Solana private keys and purchase worthless tokens while quietly routing value back to the attacker. And even here, there was no malware. The attack came from many AI agents following the same malicious instructions at the same time. These two attacks expose two fundamental limitations of automatic scanning. The first is visibility. Traditional scanners can only analyze what's in front of them, and if the malicious code is hidden behind oversized files or hosted off the platform or doesn't exist at all, especially if it's an affiliate injection and front-running attacks, then there's simply nothing to match against and it's very difficult to catch. The second is reasoning at scale. An LLM can often recognize malicious intent from natural language, but only if it can actually read the skill. Oversized files exceeded both the marketplace's scanning limits and the model's context window, preventing that analysis from happening in the first place. And even when the malicious skills were eventually reported, the attackers adapted faster than the platform could respond, and CLAWHUB automatically hid a skill after 3 reports and required accounts to be at least a week old before publishing. But attackers simply re-uploaded the same skill under a new namespace within hours, faster than those reports could accumulate. In other words, the problem wasn't a single scanner, it was that the attackers understood the assumptions every layer of the pipeline depended on and designed their skills to break those assumptions. There are 3 lessons we can take away from this CLAWHUB attack. First is treat and install AI skill as trusted code running with your agent's privileges. Even though it's just a markdown file, its instructions execute with access to the agent's credentials, file system, network, and connected services. Second is don't confuse a pass verdict with a security guarantee. A scanner can only analyze what it can actually see, and these attacks hit the payload of the platform, exceeded scanner limits, and removed the malware entirely, leaving nothing for traditional scanners to even detect. And finally, think about securing the environment and not just the skill. Run agents inside isolated containers and keep sensitive credentials away from them, and monitor outbound network requests and flag any skill that asks users or the agent itself to fetch external content or execute setup commands. So in this video, we looked at a very sophisticated attack called the CLAWHUB attack. And if you liked this video, make sure you subscribe to this channel, because creating these deep dives does take a lot of time for researching and then making these diagrams. Almost every week, I break down a real world attack like this, so make sure you turn on the notification bell icon as well. Don't forget to share this video with your friends and like and comment. And thank you so much for watching. I'll see you in the next video.